This is fundamental problem 8 from chapter 17 that says similar to fundamental problem 7. In this problem, the 50 kilogram disk is subjected to the couple moment of n times t, where t is in seconds. Determine the angular velocity of the disk when t is equal to 4 seconds starting from rest. So we're going to use the same equations that we had in fundamental problem 7. So I have the sum of the moments about point O is equal to the moment of inertia about point O times the angular acceleration. I have to find the moment of inertia about point O, but in this problem they did not give me the radius of gyration, but that's okay because I know this is a disk, and so I can turn to the back cover, and for the thin circular disk, the moment of inertia for the z-axis, which is passing through the center of the disk, is 1/2 the mass of the disk times the radius squared. So the moment of inertia, that's point O in our problem, the moment of inertia about point O is equal to 1/2 times the mass times the radius squared. The mass is 50 kilograms, and the radius is 0.3 meters. So we have for our moment of inertia 2.25 kilograms times meters squared. And now I can go ahead and sum up the moments. I have a couple moment here, which is n times t. So the sum of the moments is n times t. This causes rotation in the negative direction, so that should be negative. And I have my moment of inertia, which is 2.25 times the angular acceleration. And my goal is to find the angular velocity when t is equal to 4 seconds. Well, from this equation, I can say the angular acceleration is equal to divide 9 by 2.25, and you get 4, and this is negative, and you have the t over here too. So comparing this with what we did in fundamental problem 7, now the acceleration is a function of time, so the acceleration is not constant in this problem. So for the previous problem, we said change in angular velocity over change in time is equal to angular acceleration. That came from equation 16.2. Now we have to say angular acceleration is equal to the derivative of the angular velocity with respect to time. And this is equal to -4 t. Well, then I can bring this dt over to the other side. That would be saying d omega is equal to angular acceleration dt, and then integrating both sides. And our limits of integration are, for time, we're going from 0 to 4 seconds. And here we're starting at time is equal to 0 when the angular velocity is equal to 0. And our upper limit of integration, that's the angular velocity which we are looking for. Or I could say here, this is omega and this is t. So then putting in the -4t for the angular acceleration, when I integrate on this side, I just have omega minus 0. That is equal to the integral of -4, which I can pull outside the integral, t as I go from 0 to t with respect to t. So when I integrate that, I get t squared over 2. So that's -2t squared. So now I have omega as a function of time. I want omega when t is equal to 4 seconds. That's -2 times 4 squared, which is equal to -32. That's radians per second. And again, it's negative because the angular velocity is this way. So that is the solution to fundamental problem 8.